So we've spent some time with the first derivative and first derivative tests, and I know what's in the back of your mind. You're saying, Mr. Weaver, is there a second derivative test? And why golly, there sure is. Second derivative tells us about a graph, the concavity. The concavity is going to describe the curvature of it. So is it kind of curved up or is it curved down? And we'll talk about those later on as we get into it. So if f double prime of x is greater than 0 on the x intervals, then f is going to be concaved up. So a concave up, I guess we can go ahead and talk about what concave up is. Concave up would be something that kind of opens up. Where we have a concave down, it's going to open in the negative fashion or downwards. Can a function change from being concave up to concave down? Why, by golly, you sure can. So maybe if we have something that looks like this, so this part of our graph would be concave up. This part here, if we continue that curve, would be concave down. This point in here, very important to us. That point is going to tell us that we have a point of concavity, not concavity, point of inflection, or POI. So what are we going to do to be able to find, I guess I can go ahead and put that in there. I don't know why I didn't put it in there already. Point of inflection. So how are we going to find this concavity and these points of inflection? So here are our steps. First thing we're going to do is going to find f double prime of x. We're going to set f double prime of x equal to 0. That's going to tell us a possible point of inflection. It's not necessarily going to be a point of inflection, just like our critical points were possible critical points. Until we determine things change across them, we don't know if they're truly points of inflection or critical points. We call those POIs if you want. Going back up here, where f of x is f double prime of x is equal to 0, or where it's undefined. Be careful with that as well. Our POIs only occur when there's a change in concavity. There's points of inflection. Only occur when there's a change in concavity. So it's got to go from concave up to concave down or down to up. We can then determine our test values just like we did with our critical points. And then we test f double prime. If it's greater than 0, it's going to be concave up. Less than 0, it's going to be concave down. So here's an example that we could ask you. Find the points of inflection and determine the concavity of the graph of x times the quantity of x minus 4 to the third. So the first thing we're going to do is find the first derivative. Our first derivative in this case, we have product rule. So we have x, I didn't put my 3 in there. We'll put it on here at the end. And then times our 1, derivative of the inside, we have a chain rule there. To that we're going to add our x minus 4 to the third times 1. So what I would do is go ahead and clean this up just a little bit. We can take out an x minus 4 to the second. So here we have 3x plus x minus 4. Give me that quantity there to the first power. So that gives us an x minus 4 squared times a 4x minus 4. Then we can go ahead and find our second derivative, because it's really, ultimately, that's what we're looking for. Second derivative, we have again another product rule. So we have x minus 4 squared times 4. So that we're going to add 4x minus 4. We have a chain rule again. We have 2x minus 4 to the first times 1. At this point, we can go ahead and factor out an x minus 4. And we're going to be left with, I can also take out a 4. This is really 4 times x minus 1, isn't it? Could have done that up there, but either way, it doesn't matter. So we have 4 times x minus 4s coming out. So in brackets here, I'm going to have an x minus 4 left from my first quantity, or my first term. And to that, we're going to have an x minus 1 and a 2 from the second term there, as I've factored out. So then I get 4 times x minus 4 times, I have x plus 2x gives me 3x, and negative 4 minus 2 gives me minus 6. So I'm going to go ahead and set those equal to 0 to find my possible points of inflection. If I set those equal to 0, I get x equal to 4, and x equals, in this case, 2. So again, those are possible points of inflection. I could have some change in concavity across those points. So just like we did in our first derivative test, we're going to set up our intervals. I call them ints. We're going to start at the lowest possible value, a negative infinity. We're going to come up to 2. And then we're going to have 2 to 4, and then 4 to infinity. Again, we're working our way up to infinity. We're going to come up with some test values that are within that interval. Anytime we can use 0, good idea. So we can use 0, we can use 3, and we can use 5. I'm looking at the sign of the second derivative. So if I plug 0 in, and again, I would use the factored form because that tells me a little bit about my signs than the original derivative there, or second derivative. So if I plug in 0, the 4 is always going to be positive. This is going to be a negative value, and here I'm going to get a negative value. So a negative times a negative gives me a positive. If I plug in 3, in this case it gives me a negative. In this case it gives me a positive, so negative times a positive gives me negative. If I plug in 5, I get a positive times a positive times a positive, or positive. So this tells me that on this interval I'm going to be concaved up. A minus gives me concave down, and then a positive concave up. Notice I've abbreviated quite quickly. Normally a C up tells us that we're concaved up. More importantly, I have a point of inflection at these 2 points. I have a point of inflection at x equals 2 and 4. We can also give those values, so I can take my 2 and I can plug my 4 in to the original function to get that point out. So I plug in 2, excuse me, I have 2 times 2 minus 4, which gives me negative 2 to the third. Negative 2 to the third is negative 8 times 2 gives me negative 16. If I plug in 4, oh, isn't that a nice one? 4 minus 4 gives me 0. Anything times 0 gives me my 0. So those are going to be my 2 points of inflection if I want. Alright, so that's a nice kind of polynomial looking there. We get a little more complicated as we get into our trig. I know you enjoy so much the trig, so we'll do a problem with the trig. So we're going to go ahead and find our first derivative, f prime of x. Derivative of sine is going to be cosine of x. Derivative of cosine is negative sine of x. Go ahead and find our second derivative. Derivative of cosine is going to be the negative sine of x. Derivative of negative sine is going to be negative cosine of x. I'm going to go ahead and set that equal to 0. Well, here what I notice, I can take a negative out, so I get the sine of x equal, minus plus the cosine of x is going to equal 0. So I know that the sine of x is going to equal the negative of the cosine of x. So I ask myself, oh, where does that happen? Where is the sine of x equal to the negative of cosine of x? And again, we go back to our unit circle. In our first quadrant, we know that sine and cosine are equal to each other at pi over 4, so that's not going to work because I want it to be the opposite. But over here, at 3 pi over 4, I know that the cosine is negative and the sine is positive, opposites of each other. So my x value is going to be at 3 pi over 4. Since we're only on the interval from 0 to pi, I'm done with the values that I need because I don't need to go past the pi value or the x-axis. So I can go ahead and start my intervals, my ints. My ints, I'm going from negative infinity to 3 pi over 4. And then 3 pi over 4. Oh, I don't need to go from negative infinity. I can go from 0, can't I? And then to pi. Since again, we're only going from 0 to pi. It's restricting my domain there. So a value between 0 and 3 pi over 4. Doesn't matter what value you want. I'm going to pick pi over 2 since we know sine and cosine are pretty easy on that axis. 3 pi over 4 to pi, not as easy. We can do 5 pi over 6. So we can go ahead and look at our second derivative, the sign of the second derivative. So I'm looking at the pi of, or sine of x plus cosine of x when x is pi over 2. So I take my pi over 2, my sine of pi over 2, that's going to be 1. Oh, sorry, I come up here. I can't divide that negative out. Sorry, I get negative 1. and then minus the cosine of pi over 2, that's 0, so I get negative 1 minus 0, or negative 1. So that gives me a negative value. f5 pi over 6, we're going to have the negative of the sine of x minus the cosine of pi over 6. You throw that in your calculator if you need, or you can do your signs, but we're going to end up with a positive. So our negative tells us that we're concave down, positive concave up. We have a point of inflection, a POI, at x equals 3 pi over 4. And again, we could go ahead and put that in to our original function there, sine of x plus cosine of x, to come up with what that value is. In this case, we have the sine of 3 pi over 4 plus the cosine of 3 pi over 4. Sine of 3 pi over 4 is radical 2 over 2. Cosine is going to be negative radical 2 over 2, which gives us 0. So at 3 pi over 4, 0 if you want the actual point. Oh, lost it. All right. We also have something called the second derivative test. And this is going to talk about our relativity, our relative extrema, our relative maxes, relative mins. So, how does it work? Well, if our first derivative is 0 and the second derivative exists, if the second derivative of that value is greater than 0, then it's a relative minimum. And that might make sense to us if we think about what's happening. So if f prime of c is 0, that means that we have a horizontal tangent line. And we'll say we have that horizontal tangent line there. If it's greater than 0, we know it's going to be concave up. We can't make a concave up below this this vertical tangent or the horizontal tangent line. That's got to come up like this. So that's the only way we can be concave up and have a vertical tangent line for our f double prime to be positive. If f double prime is less than 0, if it's negative, that tells us it's concave down. So if we were concave down, the only way we could be concave down and have this as a point of horizontal tangency would be like this. We couldn't, what I'm saying is we couldn't have that line there and then be up here like this. That doesn't make sense to us because our horizontal tangent line would be way up here. If f double prime is 0, then the test fails. So if we can find f double prime and it's greater than 0, if it's concave up, we have a relative minimum. If it's concave down and we have the f prime equal to 0, we have a relative maximum. So let's go ahead and determine that relative extrema using the second derivative test. So the first thing I'm going to do is find my first derivative, which is going to be 3x squared minus 6x. I'm going to set that equal to 0. That's the first thing that has to happen. If I set that equal to 0, I can factor out a 3x, so I get x minus 2 equal to 0. So I get x equals 0 and 2. So those are my possible extrema. Now what I want to do is go ahead and find my second derivative. My second derivative in this case is going to be 6x minus 6. Now what I can do is find f double prime of these two values. So if I have f double prime of 0, that's going to give me a negative value. That tells me I have a relative maximum at x equals 0. And again, we could plug that in, get the 0.03. Likewise, if I have f double prime of 2, well, that's 6 times 2 gives me 12 minus 6. That's going to give me a positive value. Again, we're not interested in what the value actually is. Is it just positive or is it negative? Since it's positive, I have a relative minimum at x equals 2. And again, I could plug that in to get my y value if I want it. We'll go ahead and play the game. 8 minus 12 plus 3, which is going to be negative 1. So that's where our relative maximum second derivative test comes in to play. I have one more of these, and we'll look at kind of an AP question they like to test for us. Determine the relative extrema for x natural logs of x. So first derivative, I have x times 1 over x plus the natural log of x times 1. I can go ahead and simplify that. I have 1 plus the natural log of x. Set that equal to 0. Go ahead and solve for x. I have negative 1 equals the natural log of x. Change it to an exponential. E to the negative first is going to equal x. So that's where our first derivative equals 0. We go ahead and find, then, our second derivative. Our second derivative is going to be, the derivative of 1 is 0. Natural log of x is 1 over x. So that's the only value that we've got. So we have one value that could be a relative max or a min, and we have one nice, clean, easy second derivative. So we're going to find our second derivative of e to the negative first. I'm going to plug that in. I get 1 over e to the negative first. If you don't like that, we can change that to a positive as e to the first, and e to the first, that's a positive value. So since we have a positive value when the first derivative was equal to 0, we have a relative minimum. And that gives you an idea. Again, if you think about the graph of it, in order for us to be concave up, and for this point to have a horizontal tangent line, we have a relative minimum value. So how do they like to test this? Well, this is a great way of testing if you know what the second derivative test tells us. So given the following table, can we find the relative maximum or relative minimum, or is there a value such that we have a relative maximum for this function, or this function? So some things that I am interested in. Remember our relative maxes and our mins. Relative maxes and mins, doesn't matter where they're at, they're going to occur at horizontal tangent lines. At horizontal tangent lines, our first derivative, f prime of x, is going to equal 0. So we have 2 zeros in this first derivative. The next thing I'm going to look at, then, is the sign of the second derivative. If it's negative, it's going to be a relative maximum. That tells us it's occurring at, well, our x value is 2 and our y value is 3. So at the point 2, 3. Here, this 0 is going to tell us, well, right here, we have a relative minimum because of our second derivatives being positive from the second derivative test. It's a relative minimum. More importantly, it's at the point 5, 7. So it doesn't matter that we don't have a change in concavity here necessarily, because we don't know what's happening between 1 and 2 and 2 and 3, recall from our table. But we do know from the second derivative test that if the first derivative is 0 and the second derivative is negative, it's a relative max. If it's positive, it's a relative min. If it were 0, then we wouldn't know what's happening there. We wouldn't have an idea of what's going on. So that gives you kind of an idea of our second derivative, what it allows us to do. We're going to go on to curve sketching here shortly, and we're going to be able to put all this together and be able to create a nice, beautiful curve. So good luck, enjoy. If you have questions, give me a holler. Good luck.